Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory linear algebra based on my book, Retrolinear. In this lecture, we will talk about the Rank-Nullity Theorem, or what I call the dimension theorem, for both linear transformations and matrices. First, let me remind you what kernel image of a linear transformation are. I have two vector spaces, V and W. If you don't know what that is, watch my lectures on vector spaces. And you have a linear transformation from V to W. Often we say that T is linear, a linear map from V to W. Given that there are some vectors in W, W is the codomain, V is the domain, that are hit, that are the images of elements of V. That set of elements is called the image of T. Among those is the zero of W, because for a linear transformation, zero of a vector space always goes to the zero of the codomain. And then there are some vectors that are called the kernel. Those are all the elements in the domain that are mapped into the zero of the codomain. So the kernel is a bunch of elements in the domain. Which ones? The ones that get mapped to zero. Image is a bunch of elements in W. Which ones? The ones that are hit by elements of V via T. So when you apply T to elements of V, they land in places in W. Those elements that you land on, that's the image. We have proved several things about kernel and image, and so in previous videos. So let me quickly remind you. So if V and W are vector spaces and we have a linear transformation, then the kernel is not just a bunch of elements, it's actually a subspace of the domain, subspace of V. And because of that, we can talk about its dimension. And the dimension of the kernel is called the nullity of the linear transformation. The image is also a subspace, not just a bunch of elements, but a subspace of the codomain. And the dimension of the image is called the rank of the linear transformation. We also know that if you start with a basis for the domain and then map those over, then what you get is the spanning set for the image. Every element of the image is a linear combination of them. The set TV1 through TVN does not have to be a basis because they do not have to be linearly independent, but they do span. What we want to do basically in this lecture is to know what are the elements of V that we can send over so that their image is actually a basis, not just the spanning set, but a basis for the image of T. And this is for any linear transformation from P to W. We cannot talk about the kernel if T is not a linear transformation. We can talk about the image regardless of whether or not T is a linear transformation or not, but neither one will be a subspace if T is not a linear transformation. Okay, so now I can tell you what the key result is of this lecture. So we have V and W vector spaces, and we assume that V is finite dimensional. So V has a dimension, it's not infinite dimensional, it has a basis with n elements, so we're assuming that its dimension is n. And then we have a linear transformation from V to W. V again is the domain, W the target set, the codomain. Then we start with a basis for the kernel of T. Kernel of T, remember, was a subspace of the domain V. So you let S be a basis for the kernel, and then you expand that to a basis for all of V. Because that basis for the kernel is linearly independent, whenever you have a linear set of linearly independent vectors in a vector space, you can expand it to a basis for all V. That's called the expansion theorem, the subject of previous video. So you can expand S to a basis for all of V. And so what that means is you pick elements of V so that S together with them gives you a basis for V. And what this proposition says is that these new elements, the guys that you needed to add to a basis for the kernel to get a basis for the vector space, those are elements that if you send them over, they will give you a basis for the image. So this is the main theorem that we want to prove here and see some of its consequences. So let me repeat myself one more time what that says a little bit more pictorially. So I have a linear transformation from V to W. Again, V is finite dimensional, and T sends elements of V to W. So I have the image, I have the kernel. The kernel is all the stuff that goes to zero. What I do is that I start with a basis for the kernel. So I go in the kernel, walk in, find myself a basis for the kernel. So this would be a bunch of elements of V such that all of them go to zero and they form a basis for the kernel. Then what I do is I find these other elements, V1, V2, all the way till Vm, in a way that together with S, they give me a basis for V. These other elements are not going to be in the kernel. They're going to be outside. Not everything will work, but you've got to pick, you will be able to pick elements. It won't be unique. You will have a lot of choices, but you will be able to find a bunch of elements. In this case, I said maybe M elements that together with S give you a basis for V. Then what you do is you forget about S, you set, because that goes to 0, you send these other elements over and find their image. And those guys, the image of them over in W, those guys form a basis for the image of T. That's our main result. I'm going to give you the proof, but I'm going to postpone that till the end of this lecture, just so that you will see some examples and some of the main consequences. So let me give you one consequence, and I will want to figure it out before stating it. So again, we have a linear transformation. We have a basis for the kernel. We expand the basis to basis for V, and we're saying that if you find the image of those extra elements that you added to basis for the kernel to get the basis for V, you will get a basis for the image. So what? Notice something. The number of elements of S plus M is the dimension of V. Why is that? Well, because S union V1 through Vm was a basis for V. So the number of elements in there is the same as dimension. Dimension is the size of a basis. And how many elements are there? Well, there's M of them, V1 through Vm, but there's also elements of S. So the number of elements of S added to M gives us the dimension. But what is the number of elements of S? Well, that's the dimension of the kernel of T, because S is a basis for the kernel. When we put absolute value around the set, we mean its size. So the size of S is the dimension of the kernel. And we just said that if you add that to M, what's M? If the theorem is correct, then M is the dimension of the image. So if you assume that we have already proved the proposition, then we have that M is the dimension of image. So it follows from the proposition that whenever you have a linear transformation from a finite dimensional vector space to some other vector space, that the dimension of kernel plus the dimension of the image is the dimension of V. And that's what's called the dimension theorem or the Rank-Nullity Theorem. So I'm going to now state it formally. And I've just proved it to you if we knew that the proposition is true. So if V and W are vector spaces and V is finite dimensional, and we have a linear transformation T from V to W, then the dimension of the kernel plus the dimension of the image equals the dimension of the domain. That says that rank plus nullity equals the dimension. I switched the place of rank of nullity. Nullity is the dimension of the kernel, rank is the dimension of the image, but they add up to dimension of V, and this is called the Rank-Nullity Theorem for that reason. Let's do a quick example. Let's say we have a linear transformation from the vector space of polynomials of degree less than or equal to 3, that's P3R, to the vector space of polynomials of degree less than or equal to 4, P4R. So this is a linear transformation from a vector space of polynomials to another vector space of polynomials, and the rule is given by T of A plus Bx plus Cx squared plus dx cubed is that mess that appears on the screen. I have to tell you where every polynomial of degree 3 or less goes, because this is a map from P3R, and it goes to this polynomial of degree 4. Now, not every polynomial of degree 4 is in the image, so the map is not onto, but that doesn't really matter. This is a linear transformation. You would have to prove that. But the question we have is, what are the bases for the kernel and the image? Well, you know how to find those. The point is that the dimension theorem, the Rank-Nullity Theorem, will actually cut your work down quite a bit. So you start with one of them. You find one of them, but then what the dimension theorem says is that if you find one of them, then you have information about the other, which is surprising. Why is it that if you know something about the kernel, then you know something about the image, and vice versa? If you know something about the image, why do you know something about the kernel? First, let's look at the kernel. When is A plus Bx plus Cx squared plus dx cubed in the kernel? I want to know which polynomials are in the kernel. How do I find out? Well, I say, well, those polynomials are in the kernel that go to 0. So I apply t to that generic polynomial, and I get 2a minus b plus 5b minus cx squared plus 10a minus cx to the fourth, and that's going to be the 0 of the polynomial. How is that going to be the 0 polynomial? It doesn't look like the 0 polynomial, and the only way for it to be the 0 polynomial if all the coefficients are 0. So if those coefficients are 0, if this system of linear equations is satisfied, then a plus bx plus cx squared plus dx cubed will be in the kernel. If they're not satisfied, it won't be. And this you can solve in various which ways, and you can find out that for a plus bx plus cx squared plus dx cubed to be in the kernel, you have to have these two relations. B has to be twice A, C has to be 10A, and there's no restrictions on D. And so a typical element of the kernel will have some constant term, but the coefficient of x will be 2A, the coefficient of x squared will be 10A, and the coefficient of x cubed can be anything you like. So this will be the kernel. By putting A equals 1 and D equals 0, and then putting D equals 1 and A equals 0, you get a spanning set. And this spanning set is clearly linearly independent because x cubed cannot be written as a linear combination of the other guy. And so this is a basis for the kernel. And so now I know that the nullity, the dimension of the kernel, is 2. And now here's where the dimension theorem comes in and says that the rank plus nullity is the dimension of the domain. The domain here is P3R, and it's 4-dimensional because it's a basis for it is 1x, x squared, and x cubed. And if the nullity is 2, then that means that the rank is 4 minus 2, which is 2 as well. So now I know the rank is 2. So I haven't found a basis for the image, but I do know that the dimension of the image is 2, which means that to find a basis for it, all I need is 2 linearly independent vectors. And you could go and find the basis for the image in the way we would have done it before the dimension theorem. Or you could say, well, look, send T1 over, see what you get. You get 2 plus 10x to the 4th. Well, that's in the image. Send x over, and you get something else in the image. And notice that they're linearly independent. And if they're linearly independent, then there are 2 of them. And I already know that the dimension is 2. I already know that this is a basis. And because it's a basis, I can write the image of T in this streamlined fashion. In the original description of the image, you had A, B, and C. You had 3 parameters, and they were really not necessary because it was really a 2-dimensional space disguised as a 3-parameter space. And now we have written it in a much more streamlined version. It's alpha minus beta plus 5 beta x squared plus 5 alpha x to the 4th, where alpha and beta are real numbers. Again, the point is that knowing something about the kernel, if knowing the dimension of the kernel tells you what the dimension of the image is. And if you know the dimension of the image, you get the dimension of the kernel. Now, that's often helpful. And I want to prove a corollary in the case where the dimension of V and dimension of W are the same. So I have a linear transformation from one vector space to another, and it happened to be that the two have the same dimension. And I want to prove something about them. Now, before I tell you what am I going to prove, I'm going to actually prove it. And the point is that the dimension theorem actually proves things for you. You don't really even have to know what is it that you want to prove. It's so powerful that it just does things for you. Whenever you have a linear transformation from now on, the first thing you should think about is that you have the dimension theorem. Dimension of the kernel plus the dimension of the image is dimension of V. Okay, so what? Let's say that you know that T is 1 to 1. You may not know that, but what if you did? If T is 1 to 1, that's the same as saying, we've talked about this before, that the dimension of the kernel is 0. That's also sort of a slightly magical fact, that kernel controls one-to-oneness. So T is 1 to 1 if and only dimension of the kernel is 0. Okay, but if the dimension of the kernel is 0, you can put it in that dimension theorem, and what do you get? Dimension of the kernel plus dimension of the image is dimension of V. But if the dimension of the kernel is 0, that means that the dimension of the image is the dimension of V, which was the same as dimension of W. By the way, the other way works also. If you knew that dimension of the image was dimension of V, then again, the dimension theorem would force the dimension of the kernel to be 0. So T is 1 to 1 if and only if the dimension of kernel is 0, dimension of kernel is 0, if and only if the dimension of the image is the same as dimension of W. But what does it mean to say the dimension of the image is the same as the dimension of W? Image is a subspace of W. If their dimensions are the same, they must be the same. And so then that says that T is onto. And again, if T is onto, the same thing, the dimension of the image will be the same as the dimension of W. So we proved that T is 1 to 1 if and only if it's onto. So if you have two vector spaces and a linear transformation, as long as the two vector spaces have the same dimension, one-to-oneness implies ontoness, ontoness implies 1 to 1. And if you have thought about functions and have done problems about 1 to 1 and ontoness, this is surprising that somehow knowing that a function is 1 to 1, you also know that it's onto. If you know it's onto, you also know that it's 1 to 1. It only works for linear transformations, and it only works if the dimension of the domain and the codomain are the same. Okay, now we're going to apply the dimension theorem to one particular kind of linear transformation, matrix transformations. We have said that whenever a matrix walks through the door, one of the things we like to do is to think of it as a linear transformation. And the linear transformation then follows whatever we know about linear transformations, in particular the dimension theorem. So let's see what it says about matrices. So A is an m by n matrix, and then I'm not going to tell you what I'm going to prove until I prove it. But again, when you see a matrix, you think of a linear transformation. What linear transformation? The linear transformation that goes from Rn to Rm. What's n? The number of columns. What's m? The number of rows. And the rule for it is that what do you do to x? X is an element of Rn. X is not a number. It's a column vector. LA of x is a times x. And we have seen that this is a linear transformation. So you just take x and multiply it by a. A is m by n. X is n by 1. And so when you multiply them, you get m by 1. You get something in Rm. This is the way we think of a matrix as a function. And as a function, it's a linear transformation. Therefore, we can apply the Rank-Nullity Theorem or the dimension theorem. And so by dimension theorem, dimension of the kernel of LA plus the dimension of image of LA equals n. But in a previous video on matrix transformations, we saw what the dimension of the kernel is. The dimension of the kernel is the nullity of the matrix, the dimension of the null space of the matrix, and the dimension of the image is the rank of A, the number of linearly independent rows or the number of linearly independent columns, which happen to be the same. So we now proved something about matrices that does not mention linear transformations. If A is an m by n matrix, then the rank of A plus nullity of A is n. And that's also amazing just by itself, because it says if you know the number of linearly independent vectors, then you know what the dimension of the null space is, and vice versa. If you know the dimension of the null space, you already know the rank of the matrix. Okay, now if this was the only thing you were interested in, the proposition that I stated at the beginning in terms of linear transformations and what elements go over and give you a basis is just sort of a more general fact. But if this was the only thing you were interested in, the Rank-Nullity Theorem for matrices, then we could argue in a different way. So I'm going to try to give you an argument that way. There's one part of it that you sort of have to believe me. And in fact, you can think of the dimension theorem as a proof of that, although you could make it precise as well, just by looking at matrices. So let's say A is an m by n matrix, and I want to see why the Rank-Nullity Theorem would be true. Now, if you haven't thought about A as a linear transformation, the thing you would think of A as is as a matrix that has different spaces. They have column space, row space, null space. And you also always like to look at the reduced row echelon form of A, because that has a lot of information about A. So let R be the reduced row echelon form of A. So R is also m by n, is the matrix you get by doing a whole bunch of elementary row operations until the matrix in a reduced echelon form. Again, previous videos talk about those. And we know that when you do elementary row operations, the null space and the row space do not change. And therefore, the rank of the matrix A is the same as the rank of this reduced row echelon form of it. Rank of A is the same as rank of R. The nullity of A is also the same as the nullity of R. So what? So we can think about rank and nullity for this reduced row echelon form matrix. And for R, the matrix that it's in reduced row echelon form, what's the rank? It's the number of leading ones, because that's the number of linearly independent rows or columns, because those rows that have a leading one cannot be linearly dependent, because every one of the ones is staggered in a different place, and it's zeros in its column. So there's no way to find linear combination of the other columns to get that one row. And other than the rows with leading ones, you only have rows of all zeros. So the rank is the number of leading ones. Now, the number of leading ones is also the number of basic variables, and the number of non-basic variables, which is the other variables, is going to be the same as dimension of the null space. Those are, if you remember how we solve systems of homogeneous systems of equations, those non-basic variables are the ones that are free variables, and you can say, well, this one can be anything you like, that one can be anything you like, and so on. And you write things you write all the basic variables in terms of them. Now, this is the part that I say is a little bit shaky, is that why is that exactly the dimension? Well, you can make that precise, as I said, by thinking about the fact that how you write the basic variables in terms of the non-basic variables and making sure that everything is linearly independent. Like you can get a basis for the null space by making every non-basic variable equal to 1 and everything else equal to 0. And that needs a little bit of thought. But this is actually a proof of that too, because we already know that the dimension theorem is true. Okay, so if that's the case, then clearly the number of basic variables plus number of non-basic variables is the number of columns, because every column is associated with one of the variables, and the variables are either basic or non-basic. So either you have 3 variables or not, and so that's what it is. But see what we said. The number of basic variables is the rank. The number of non-basic variables is the nullity, is the dimension of the null space. And so we have the rank nullity. The number of the rank of the matrix plus the nullity of that is the number of columns. Okay, so now finally, let's prove what we want, the proposition that made all of this possible. So we have a linear transformation, we have a kernel, and we have a basis for the kernel. We have expanded that to a basis for V. And what we want to prove is that if I send these guys over, I get a basis for the image. Okay, I'm going to spin my wheels a little bit and talk around this. And then in the next slide, I will do the main part of the argument that needs to be done. So first of all, dimension of V is n. V was a finite dimensional vector space, and dimension of the kernel is k. I'm going to just give those names, so I don't have to keep saying dimension of V, dimension of the kernel. And S is a basis for the kernel. The kernel is k-dimensional, so let's say that the elements in the basis are U1 through UK. Okay, so this is our setup. And if k is 0, if it happens that the kernel is just the 0 vector, then S will be the empty set. That's what I mean by that. That's a convention that I will take. Now, let's do one case separately. So if k is n, what does that mean? That means that the dimension of the kernel is the same as the dimension of the domain. That means that everything is in the kernel. Kernel T is V, and that means that everything goes to 0. So in that case, image of T is the 0 vector. The only thing that's hit is the 0 vector. Is my theorem true in that case? Well, in that case, when I want to extend S to a basis for V, I don't really do anything. S is already a basis for V. So that V1 through Vm is an empty set. And so this set is the empty set, because when I want to find, when I want to go through these extra elements and find their image, there's nothing to find. So I don't find anything on the other side. And the empty set is a basis for the image. So in this sort of almost ridiculous special case, the theorem works as long as we think about the empty set as a basis for the image, so we don't have to make a special case for that. Okay, so now for the general case, I have U1 through UK and V1 through Vm together are a basis for V. The first ones, the U1 through UK is a basis for the kernel, and then I added these guys in to get a basis for V. Now I know that if I have a basis for V and if I apply T to them, I do get a spanning set. So image of T is the span of this. This is a theorem that we proved in the video on span, that if you take a basis for the domain and send it over, you get a spanning set for the image. Not necessarily basis though. But T of U1, T of U2, T of UK, what are those? Well, those are 0. Why is that 0? Because they're in the kernel. So what does that say? Now, do they help in terms of spanning the image? No, they don't. They're just the 0 vector. So you throw those out and you're left with T of V1 through T of Vm. So you now know that the image is spanned by these guys. We want to show that T1 through Tvm is a basis. And for that, I need 2 things. Do they span? Are they linearly independent? And I just showed you that they span. Because, I mean, I didn't show you, it was sort of obvious, because of the fact that the U1s the U's did not really help. And so these guys have got to do the spanning all by themselves, because we know that whenever we have a basis and send it over, it's going to span the image. And if the U's aren't going to help, the V's got to do it all by themselves. So the T of V1 through T of Vm, I already know that they span. So all that remains to show is that to show that this set is linearly independent. And that's sort of at the heart of the proof. Why is it that when I send these guys over, I get a linearly independent set? I already knew how to find spanning sets, but sending a set in that spans and is linearly independent was the issue. And we found out that these guys span, but why are they linearly independent? Okay, so what's the setup? I've got a linear map. I've got a basis for the kernel. I've expanded it to a basis for V. And now I want to show, and the only thing I need to show, and if I do this, the proof is complete, that T of V1 through T of Vm is linearly independent. How do I prove that a set of vectors is linearly independent? I have a variety of ways, but the definition says, write a linear combination of them equal to 0. Assume that alpha 1 times T of V1 plus alpha 2 times T of V2 all the way till alpha m times T of Vm is the 0 vector. And then show that the only way this could have happened is if you cheated and used scalars that were all zeros. Of course, if the scalars are zeros, this works. That's not the point. The point is that there's no other way of writing a linear combination equal to 0 other than using the 0 vector. So I have to show that there's no other combination of alpha 1, alpha 2 to alpha m that gives us the 0 vector other than it being 0. Okay, what am I going to do? So now here's where the fact that T is a linear transformation comes in. If you have this linear combination of T's equal to 0, because it's a linear transformation, you have an irresistible urge to combine all of them together. And so because T is linear, you can write T of alpha 1 V1 plus alpha all the way till alpha m Vm equals the 0 vector. Why? Because T is linear. This statement here, T of alpha 1 V1 plus 3 dots plus alpha m Vm, splits up into T of alpha 1 V1 plus T of alpha 2 V2 plus T of alpha 3 V3 and so on. And then the alpha 1s, the scalars come out, and you get alpha 1 T of V1 plus alpha 2 T of V2 plus alpha 3 T of V2 all the way till alpha m T of Vm. And that's the 0 vector. So this is 0 vector. So this left-hand side is the same as the old left-hand side. Okay, so what? Now I've got this thing here, T of something that went 0. Think of that as an apple. T of apple is the 0 vector. How could that be? Oh, that means apple is in the kernel. Doesn't mean that it's 0, but it's in the kernel. So this guy is in the kernel. I'm not done yet. So what about the kernel? But now I remember that I had a basis for the kernel. What? S. S was a basis for the kernel. If this guy is in the kernel, it should be a linear combination of the basis elements. So I should be able to find some scalars to write those together. So what's wrong with this picture? What's wrong with this picture is that the U's and the V's were linearly independent. And so you should not be able to write a linear combination of V's equal to a linear combination of U's. You can bring them all one side, and that means you wrote all the linear combinations equal to 0. You can't do that unless you cheat and all the scalars are 0. So then that means that all the scalars are 0. I don't really care about the betas, but the alphas are 0, and that's what I wanted to prove. And that proves that this T of V1 through T of Vm, which were the images of those extra elements that I added to the kernel to get a basis for V, those guys are linearly independent. If they're linearly independent, we already know that they span, so they must be a basis for the image. And this lecture is over. And we'll see you in the next lecture when we will talk about isomorphisms.